Alrighty, howdy folks. Chapter 3, Section 6, that's going to be the focus. And it's about derivatives of logarithmic functions. Whoa, let's see what this is all about. What's the derivative of natural log of x? Simple question, right? Again, natural log of x is a very common function. You will see this quite a bit in all kinds of engineering stuff and in calculus 2, differential equations and all that. So we really need to know what the derivative of natural log of x is. Okay. How should I put it? Okay. One thing is true. You can always start with that definition of the derivative. Because this natural log of x is something that we don't know anything about, what its derivative is. So you could go, maybe I'll try natural log of x plus h minus natural log of x all over h and see if I can figure out the derivative that way. You can give it a shot, but I don't know. So a simpler way does exist, fortunately. So let's do that. Here, if we let y equal natural log of x, right? Do you remember this concept of if y is natural log of x, then can you figure out what x itself must be? And the question makes sense. Y is natural log of x, so what should x equal? Well, going from the logarithmic form to exponential form tells you that x must be equal to e to the y, right? So that implies e to the y equals x. Or another way of arriving at the same answer is y equals natural log of x. So raise both sides to the power of e. So on the left hand side we would have e to the y, on the right hand side e to the natural log of x. But then there's a property of logarithms that says a to the log x to the base a is x, or e raised to natural log of x is just x, right? A raised to log x to the base a, or a raised to log base a of x, people write like that, is just x. So e to the natural log of x being x, we can write e to the y equals x. Okay, how's that going to help us find the derivative of natural log of x? Well, we need to find d dx of y now. So the whole problem boiled down to finding dy dx or y prime. So can we differentiate both sides with respect to x? And when we do, what's the derivative of e to the y but with respect to x? Right? Chain rule. Differentiate with respect to y itself first. So you get e to the y times y prime. So e to the y times y prime, or dy dx. On the right hand side, the derivative of x is just 1. So e to the y dy dx equals 1. So dy dx equals 1 over e to the y. But e to the y happens to be x. So dy dx equals 1 over e to the y equals 1 over x. In other words, the derivative of natural log of x is 1 over x. Okay. Now, let me put your minds at ease. Am I expecting you to derive this? No, I'm not. What I definitely want you to know is, have some idea. Be curious about, hey, how do people figure out derivative of natural log of x? And so go through this procedure, and if you can remember, do it. Otherwise, don't worry too much about it. Definitely, however, you must remember the result. The derivative of natural log of x is 1 over x. And in fact, the derivative of natural log of absolute value of x is equal to 1 over x. I'm not going to prove that to you or anything like that. Just take it from me. Derivative of natural log of absolute value of x is 1 over x. Cool? All right. Now, with that, let's ask. The derivative of natural log of x is 1 over x, fine. But what in the world is derivative of log base b of x? Right? When the base is e, that's the natural logarithm. But when the base is not e and it is something else, some other base b, well, do you remember that something called change of base formula? What is the change of base formula? If you have log base b of x, you can change the base from b to whatever you want. For example, conveniently, we could change it to e, right? And when you do that, you can write log base b of x as natural log of x over natural log of b. I'm sure you must have seen this in pre-calculus, right? When somebody wanted you to find out what's the log base 7 of 54. In a calculator, some calculators do have any base, but in most calculators, you can only do log base 10 or natural log. So there, you must have used this change of base formula. Look at how handy that is. That has come right now. Okay. So log base b of x is natural log of x over natural log of b. So when we need to differentiate log base b of x, we'll apply the change of base formula d dx of natural log of x over natural log of b. But natural log of b is just a constant because b is a constant. So we can yank that 1 over natural log of b, that constant multiple, outside of the derivative, and that's what I did, times the derivative of natural log of x itself, which is 1 over x. So derivative of log base b of x, you must remember this also, is 1 over natural log of b times 1 over x. If you cannot remember it, at least know the change of base formula and be able to derive this for yourself. Cool. All right. Next, applying chain rule. How do you apply chain rule to derivatives of logarithmic stuff? Well, the same way. d dx of natural log of u, if you want to find that, first find d du of natural log of u and then multiply by du dx. Isn't that something we did all the time while applying chain rule? It's the same idea. Okay, d du of natural log of u times du dx. Okay, and that is equal to 1 over u times du dx. Cool. Now we'll apply that to quite a few problems. I can say, what's the derivative of natural log of sine square x? Since we don't have a simple natural log of x, we have something more complicated. I'm going to look at this as natural log of u, the sine square x as u. So I have natural log of u. And the derivative would be 1 over u, that is 1 over sine square x. Would you agree? Natural log of u, the derivative is 1 over u. So that means natural log of sine square x is the first step, is 1 over sine square x times the derivative of u itself, that is the derivative of sine square x itself. Right? By now, you must have been really good at applying chain rule. Sine square x, what's the derivative? How do you figure out the derivative of sine square x? Remember, I said anytime you see a trig function raised to some power other than 1, always think of it as sine x, the quantity square, or the trig function raised to that whatever that quantity is. So look at this as sine x, the quantity square. And the moment you look at it that way, you should think of it as u1, the quantity squared. And so apply the power rule. So 1 over sine square x times the derivative of the quantity sine x squared is 2 times sine x. times the derivative of sine x itself, which is cosine x. Right? I'm taking time to talk about a simple derivative of sine square x. I shouldn't be. By now, you should be like, oh, come on, that's obvious, man. I have done more complicated problems than that, so don't worry about it. That's the way you should be. Okay, cool. 2 sine x, and I could have simplified this, right? Could have made it 2 cosine x over sine x. And in turn, I could have made it 2 cotangent x. Wow. Okay. Ooh, I like this one. Natural log, derivative of natural log of the quantity x plus square root of x square minus 1. This is a pretty interesting one. All right, you tell me. First step, natural log of u, right? Because this is not a simple x, it's a more complicated x plus square root. Think of it as u. So derivative natural log of u, first step, 1 over u, 1 over x plus square root of x square minus 1, times the derivative of x plus square root of x square minus 1, right? The derivative of u itself. Well, if you look at the u, there's a summation going on, x plus something. So, the derivative of the first term plus the derivative of the second term. Derivative of first term, x, simple, 1, plus, what's the derivative of square root of x square minus 1? Because it's not a simple square root of x, my attitude is, I'll think of it as square root of u1. Because we already said u was x plus square root of x square minus 1, I would just want to give a different variable, u1. So we have square root of u1. Oh, simple. 1 over 2 square root of u1 times the derivative of u1 itself. What's u1? X square minus 1. What's the derivative? 2x. So I put all of these things together and I said the derivative of x is 1 plus the derivative of square root of u1 is 1 over 2 times square root of u1 times the derivative of u1 is just 2x. Cool? All right. Then we could leave it like that, but something absolutely fascinating happens if we actually simplify this. So look at the next steps. Then I said, well, the 2's, 2 over 2 is just 1. So x over square root of x square minus 1, right? Now, can I add these two fractions, 1 plus x over? That's what I did in the next step. I left the outside one the same, didn't touch that. But then, okay, maybe I could have put it this way. Multiply both the top, multiply yeah, multiply and divide by square root of x square minus 1. Nah, okay. Add the fractions. It's better to say it that way. And so when you do that, you get square root of x square minus 1 plus x over square root of x square minus 1. Right? Okay. And so, lo and behold, this numerator is exactly the same as this denominator over here. So they divide up into to give us 1, right? This numerator over this denominator is equal to 1. So we just end up with 1 over the quantity square root of x square minus 1. Fascinating. Now, Let me give you a bit of a heads up. So far we have been, please pay attention to this. So far we have been working on derivatives of things, right? But pretty soon we would be figuring out what are called antiderivatives. That means we'll be going backwards. I just want to give you a heads up. We are not there yet, but if I tell you that, maybe as you are memorizing, you might want to ask yourself the opposite way as well. Meaning, the derivative of sine x is cosine x. So what is the antiderivative of the right hand side, the cosine x? The answer is sine x. That makes sense. The derivative of sine x is cosine x. So the antiderivative of cosine x is sine x. Now, it looks like, based on that concept, the derivative of natural log of x plus square root of x square minus 1 is 1 over square root of x square minus 1. So the antiderivative of 1 over square root of x square minus 1 turns out to be this natural log of x plus square root of x square minus 1. You don't need to memorize this, but I'm just giving you a heads up. When you come to calculus 2, this would be one of the problems. We don't say antiderivative, we say something called integral. What is integral of 1 over square root of x square minus 1 dx? And we go through a big long procedure and then say and show that in fact that is equal to natural log of x plus square root of x square minus 1. But it's fascinating to see that in fact the derivative of this is this. Okay? Once again, folks, if you understood it, great. If not, don't worry about it. But you just, the antiderivative part, if you didn't understand, right now don't worry about it. Cool. Next, derivative of natural log of cosecant x minus cotangent x. What an interesting thing. Good. How should we look at it? Look at it as natural log of u, ddx of natural log of u. What is u? Cosecant x minus cotangent x. Cool. That means first step, 1 over u. 1 over cosecant x minus cotangent x times the derivative of u itself. Cosecant x, the derivative is negative cosecant x cotangent x. The derivative of cotangent x, negative cosecant square x. So making it negative cosecant x cotangent x minus negative cosecant square x became plus cosecant square x. Right? Okay, what's the big deal about that? The big deal is, can I factor out a cosecant x out of these two terms? And when we do, what do we end up as? What do we end up with? We have cosecant x times cosecant x minus cotangent x over this denominator. That's what I wrote. Lo and behold, cosecant x minus cotangent x over cosecant x minus, hey, that just divides into 1, leaving us with a simple cosecant x. Isn't this fascinating? So the derivative of natural log of cosecant x minus cotangent x turns out to be a simple cosecant x. And now, in light of what I just said about the antiderivative, isn't it fascinating that the antiderivative of cosecant x is natural log of cosecant x minus cotangent x. In fact, it turns out to be absolute natural log of absolute value of cosecant x minus cotangent x. But here we go. Right? Alright, next. The derivative of natural log of square root of a square minus x square over a square plus x square. The moment I say it, two ideas come. In fact, I'm going to do this problem by two different ways. Okay. First method is, it looks like natural log of u. So 1 over u times the derivative of u. 1 over the whole thing, this times the derivative of this square root of something. Wait a minute. Derivative of square root of, let's call it u1. Please be clear in your heads. u1 is what? The stuff inside the radical only, not the radical. Because we are looking at this as square root of u1, don't put in u1 again, do not put as that radical, that square root. u1 is just the inside stuff. Keep that in mind. Cool. So square root of u1 is 1 over 2 square root of u1. So 1 over 2 square root of u1 is that inside stuff. So that's what I wrote. I'm insisting on this thing about, hey, the u1 is the inside part because that's what we need to differentiate next. We need to multiply this by the derivative of u1, and the derivative of the u1 is just the inside stuff, right? Okay, what's the inside stuff, the derivative of this? Well, for that we need to apply the quotient rule, and that's exactly what I did. Denominator times the derivative of the numerator minus numerator times the derivative of the denominator over the square of the denominator. Low d high minus high d low over low low. Cool? All right. Now what? Oh man, what happened to this? It doesn't look like that. I see. I think when I copied it from my desktop to this one, that's when it became like that. Okay. So here, what did I do? Well, looks like what I did here is I recognize that there's a square root of this guy times square root of the same guy. So when we multiply square root of a times square root of a is just a. So that's what I applied here. Maybe I should have said p, square root of p times square root of p is just p. So this is 2 times that stuff. So we are done with the first 2 terms, simplified to this guy. And here, this one, let's see, minus 2a square x, and there is another minus 2a square x. That becomes minus 4a square x, but then a negative 2x cube here and plus 2x cube, they add up to 0. So this whole numerator simply reduces to negative 4a square x over that denominator square. Now let's see if we can simplify this any further. Well, do you notice that there is an a square plus x square here and a square plus x square, the quantity square here? Would that simply reduce to a square plus x square here? That's what I wrote. And then 2 went into negative 4 to give me negative 2 a square x over a square minus x square times a square plus x square. And we could have written this as a to the 4 minus x to the 4. Oh, I did do that. Okay. So that's the derivative after simplifying. And your WebAssign thing seems like it expects you to simplify things. That's why I thought I'll go ahead and show you all kinds of simplifications. It's a good exercise. I mean, I know it may be a bit frustrating, but it's a wonderful practice. Next, I promised you I'll show you 2 different methods. Now check this out. To find the derivative of something like this, we could have recognized that, hey, wait a minute, natural log of square root of something, the square root means this quantity raised to 1/2. right? A square minus x square over a square raised to 1/2. But that exponent 1/2 becomes the coefficient of natural log. That's exactly what I did here. Cool. And are you guys hearing snoring? My dog is sleeping right next to me and she is snoring. Oh Lord. 1/2 natural log of a square minus x square. Cool. Well, what's the big deal? Why did you do that, man? Now check this out. We can recognize that natural log of p over q is natural log of p minus natural log of q. So we can write this as 1/2 natural log of a square minus x square minus natural log of a square plus x square. And this, I want to say, is much easier to differentiate because of the subtraction. There is no need for any quotient rule or anything like that. Natural log of a square minus x square, the derivative is 1 over a square minus x square times negative 2x. What's that? The derivative of a square minus x square. Similarly, natural log of a square plus x square, the derivative is 1 over a square plus x square times the derivative of a square plus x square itself, which is 2x. That's what I wrote here. Cool. And then I can factor out a 2 out of both the terms, and that 2 over this 2 is just 1. And we can also factor out an x to leave us with this, and then when you add the two fractions, it simplifies to what we had earlier. All right, so two different methods to solve the same problem. Okay, and then find dy dx and d square y dx square given y equals natural log of absolute value of secant x. Let's look at this. Dy dx is just d dx of the y, which is natural log of absolute value of secant x, and that's 1 over secant x times the derivative of secant x, which is secant x tangent x. Cool, so we got the first derivative. Well, don't move on to the first derivative yet, second derivative yet. Just simplify this. Secant x, right? That just becomes tangent x. Ha! Now the second derivative, piece of cake. What is the second derivative? The first derivative of the first derivative. So d dx of dy dx, dy dx being tangent x, we get d dx of tangent x. Right? That's equal to secant square x. It's as simple as that. Now, this is an interesting problem. Differentiate f and find the domain of f if f of x equals natural log of natural log of natural log of x. What? Natural log of natural log of natural log of x. Yikes. Yeah, this is a good one. You will in fact see a problem like this in calculus too. So that's why I picked this one. Okay. Well, this is as simple as natural log of u. What is u? This inside stuff, natural log of x. That part is the u. So natural log of u is 1 over u times the derivative of u itself, the derivative of natural log of x. Well, that's natural log of u1. So 1 over u1 times the derivative of u1 itself, that is derivative of natural log of x itself, that is 1 over x. You see how we split this? First, we looked at this as natural log of u1. What is u1 consisting of? It consists of natural log of some u2. And u2 is natural log of x and its derivative is 1 over x, like that. Cool. The differentiation is an interesting one. But then find the domain. I'm not going to ask you this in a test though, but I just want you to see it. To find the domain, we'll proceed in steps. For this, I'm going to start inward. I'm going to start with this natural log of x and then keep going outwards. So, first we have to have a natural log of x to be greater than 0. We want x to be greater than 0, otherwise natural log of x is not defined, right? Natural log of negative numbers is not defined. So x must be greater than 0 so that the innermost natural log of x can be figured out. Cool. Now, for the second one, its argument is natural log of x. So this natural log of x better be bigger than 0, right? Natural log of x better be bigger than 0 so that natural log of x can be defined, is defined. Okay, now what does it mean to say natural log of x is greater than 0? What does it mean to say what should x be? Do one thing. Raise both sides to the power of e. So e to the natural log of x is greater than e to the 0. Cool. E to the natural log of x is greater than e to the 0. But what is e to the natural log of x? X. What is e to the 0? 1. Aha. So that means x must be greater than 1. Cool. All right. Then earlier we got x should be greater than 0. Now we are restricting the domain even more and we are saying no, it's not enough. If x is greater than 0, x must be actually greater than 1. Okay, proceeding in that same fashion, to be able to figure out the outside natural log of natural log of x, this natural log of x must be greater than 0. Okay, what does this mean in turn? Well, again do the same thing. E raised to natural log of x must be greater than e to the 0. Okay, that is natural log of x must be greater than 1. So that means natural log, e to the natural log of x must be e to the natural log of x is just natural log of x, so that should be greater than 1. And that means x must be greater than e in turn. So the domain is e to infinity. If you didn't understand this domain part, don't worry about it. I'm not going to ask. But it's an interesting one. Cool. That's it, folks.